Harry, please get us underway.
Thank you, Alasdair. Well, good morning all, and welcome to the 14th LISA Symposium, where I see my first error is in having my background the wrong way around. So welcome. We're going to start with a few words of introduction from Martin Hendry, as the chair of the LSAC and also as a senior member of GU, who will welcome you to this jointly organised GU and UK ATC symposium. So I'll hand over to Martin.
Thank you, Harry. So I'm going to risk further gremlins by sharing my slides. Hopefully this will work. And just go through the careful steps to make sure I do it correctly. And okay, I think that should have worked and I should have appeared in the lower part of the screen. Excellent. So good morning, everyone. I'm joining you today wearing two hats, as Harry has mentioned. First as chair of the Scientific Organising Committee for the symposium, and second as Clerk of Senate and Vice Principal of Glasgow University, which I formally don't take up that position until August 1st. So you're getting me a week early wearing that hat. And it's really in that latter capacity that I'd like to, first of all, to formally welcome you all to the 14th LISA Symposium on behalf of Glasgow University and the UK Astronomy Technology Centre in Edinburgh. So the UK ATC is a national centre of excellence for the development of scientific instrumentation and facilities for ground and space-based astronomy. It's based at the Royal Observatory in Edinburgh, and it's operated by the Science and Technologies Facilities Council, which is part of UK Research and Innovation. And it has a world-leading reputation for delivering innovative and capable cameras, spectrometers, and telescope systems. And the ATC works with leading organisations such as ESO, ESA, and NASA to answer fundamental questions about the origin and evolution of stars and planets and galaxies. And one of its highest profile recent projects under the leadership of its current director, Professor Gillian Wright, as European PI, has been construction of MIRI, the mid-infrared instrument for the James Webb Space Telescope. And we're delighted that Gillian will join us on Wednesday to give a plenary talk about JWST. And ATC is also playing a major role in the development of LISA. The ATC and the University of Glasgow are the lead partner developing and building the optical system of the laser interferometers that will be at the heart of LISA. So turning now to our other co-host, the University of Glasgow. We are a top 100 research intensive university that's been changing the world since 1451. We count among our alumni major historical figures in science, such as James Watt and William Thomson, or Lord Kelvin, and more recently Jocelyn Bell Burnell, and indeed the 2021 Nobel laureate for chemistry, David Macmillan. And gravitational waves are part of Glasgow's research beacons, and our work is carried out within the Institute for Gravitational Research in the School of Physics and Astronomy. And as I'm sure you will all know, there's a long history of gravitational wave research in Glasgow, from the pioneering work of Ron Drever and Jim Huff in the 1970s, through to our major role enabling the first LIGO Virgo detection in 2015, and the exciting discoveries that have followed since then. Now, 2015 was also a major milestone for Glasgow's work on space-based gravitational wave detectors, with the launch of LISA Pathfinder. Under the leadership of Harry Ward, our session chair this morning, the Glasgow LISA team built the ultra-stable optical bench for LISA Pathfinder, and will use that expertise in partnership with the ATC to construct the optical benches for the LISA mission. So the University of Glasgow is very proud to be co-host of the 14th LISA Symposium, and I personally was very proud to chair the Scientific Advisory Committee. So I'd like to thank all of the members of the SAC for their hard work in assembling our programme of plenary and parallel sessions over these past few months. I believe we've put together an exciting, topical and timely symposium programme that will highlight just how far the LISA mission has come on its journey towards launch next decade. So very shortly, we'll begin with an overview of the current LISA status from Martin and Oliver and Linda. And then we'll have a short break, and that will be followed by a plenary talk from Monica Colpi on electromagnetic signatures of LISA massive black hole binary coalescences. And then we'll round off this first plenary session with a plenary on time delay interferometry for LISA from Jean-Baptiste Bayle, recently joined us in Glasgow and previously in JPL Caltech. So I won't read through all the other sessions, but the exciting nature of the programme will unfold over the course of this week. We'll be back again this afternoon at 1500 Central European time with our second session, another block of plenary talks. But I just want to highlight the fact that when we move on to tomorrow, we have a plenary session tomorrow afternoon, European time, but that will then be followed by a series of parallel sessions tomorrow evening, European time. So we're mixing up the timing of the sessions a little bit to do our best to accommodate the many time zones of the participants across the world. On Wednesday, we return to a morning European time plenary session, again led off by Gillian Wright, whom I mentioned before. And then we have another round of parallel talks beginning at 1500 European time on Wednesday afternoon. Moving on to Thursday, we switch things up a little bit. We've then got a parallel session in the afternoon European time, so the parallels come before the plenary block on Thursday. And our plenary session on Thursday evening European time will include some fascinating personal reflections on the LISA journey by Tuck Stebbins and Bernard Schutz, looking at the many decades of LISA's journey towards the point we've now reached, and indeed looking ahead to the exciting times that will lie in the next decade as we approach launch. And then finally on Friday, we have our final block of plenary talks in the morning European time before rounding things off with our final, I think I said plenary talks before, our final block of parallel talks on Friday morning, and then our final plenary session on Friday afternoon European time, in which we'll begin with a plenary on the Event Horizon Telescope, another extremely high profile mission, extremely high profile project in the field of relativity and fundamental physics. And we'll have a talk on waveforms for LISA and 3G ground-based detectors before our final major talk is in fact a panel discussion looking beyond LISA. It will be focusing on the papers that were in the field of gravitational waves contributed to the ESA Voyage 2050 process. So we have a stellar lineup of panelists for that, and that should take us through to about 17:30, 17:35 on Friday afternoon European time, when our closing remarks will be delighted to be joined at that point for a few remarks from Karsten Dansman. So that gives you a very top level overview, but I do encourage you to look at the programme to, of course, join us for as much as you possibly can. But please be assured we are recording all of the plenary and parallel talks. They will also be live streamed on YouTube, and they'll be available for watching as a legacy after the symposium is completed. So I'm going to pass on to Alasdair now, who'll say a little bit more about the IT setup, both in terms of the plenary and the parallel sessions. But again, a very warm welcome from the University of Glasgow, and I hope everyone enjoys the symposium.
Thank you, Martin. So hopefully all the technical aspects of this will go along smoothly. We had a small delay in the stream beginning, but that should be sorted. And as Martin mentioned, the recordings and streams will be available on the LISA Mission YouTube channel. As a participant, we're simply looking for you to engage and ask questions during this symposium. We can't promise that all questions will have time to be answered, but please ask. And if you'd like to raise your hand, if you want to ask your question verbally, that's fine, although it is at the chair's discretion as to whether those questions will be answered. So pop your questions into the Q&A box if it's a plenary session like this, or into the chat if it's a parallel session. If there are any problems or any technical issues, you can either communicate to the IT host of the session you're in via your chat or the Q&A box at a push, or you can use the symposium email address to contact us. There's a skilled team of people here dedicated to ensuring that this all goes smoothly, and hopefully it will. So sit back, relax, and enjoy. Back to you, Harry.
You're muted, Harry. Let me be the first to say that. No doubt it will be said many times this week.
Thank you. Thank you, Martin, and thank you, Alasdair. We're almost on time, and we're ready to begin the first of the plenary sessions. And we're going to start with an overview of the current LISA status. And this is going to be a tripartite show, I believe, with Martin Hewitson from Hannover, and then two colleagues from ESTEC, Oliver Jennrich and Linda Mondin. And I don't know how they're going to split it up, but I'll pass over in the first place probably to Martin, I would guess.
Not quite, Harry.
Not quite.
Okay. I think we agreed that I shall start. This is Oliver. I try to share my screen. That's always exciting. There you go. With a piece of luck, you see the right screen. Shout if you see the presenter's view. So I've been asked to give we have been asked to give an overview of the LISA status. I'm Oliver Jennrich. I work for the European Space Agency since more than 20 years now. I'm one of the LISA study scientists here. The other one is Nora Lützgendorf, who is still in Baltimore, so she might show up a little bit later, or she might already lurk in the background. And I have to say, I borrowed quite a lot of slides from our study manager because it's a status talk, and normally I'm not doing that. But let's dive right in. This is the LISA Symposium. I assume everybody on this call knows what LISA is, what gravitational waves are, and what the science of gravitational waves are. If not, you're in for a lot of learning over the next week, so pay attention. If so, I won't bore you with the details here. And sometimes you hear history going all the way back to the prehistorics. I'll leave that to Tuck at the end of the week. I'll start here with the more recent history that we had in 2017. The proposal for the LISA mission was yet again submitted to ESA, and it was answering the call for the third large mission, and it was by no big surprise selected by the ESA Science Program Committee. It was not really an open call, that one. So briefly after that, in 2018, we kicked off Phase A. I'll tell you a little bit later what Phase A is. But suffice it to say for the moment that we finished Phase A last year, end of last year, with what we call the mission formulation review. And I want to tell you a little bit about what has changed between the proposal submission and the closeout of Phase A. There are a number of things have changed, is one way of putting it, and I prefer developed, because you see it is a evolution and not a radical change. We had to address the performance, we meaning the study team here at ESA and the science team. And the reason for that was partly a little bit formal. The proposal had the statement that there were requirements and goals. Old hands will remember that we always had goals, usually in the low frequency range and the high frequency range. Now, goals are not standard in ESA, so nobody really knows what goals are. I mean, everybody understands the word, but if you become formal about it, then nobody really knows what it means. So we said, okay, together with the science team, let's adjust the sensitivity range, require it to be from 0.1 millihertz to 1 hertz. But we also still have we still ask industry to monitor low frequency performance. So if there's anything dramatically going wrong, which they should tell us, which is pretty much what we thought a goal will be, but we avoided that word by now. One other important thing that happened, that the ESA Athena mission became a source or a partner of potential synergies. In the sense of that LISA might be able to give a pre-warning for an imminent merger to Athena, and Athena might want to look at the source of that merger or the merger and see if they can capture a couple of X-rays there. That has some small operational consequences. We had to adjust a little bit our how we deal with space to ground and ground to space communications, and the overall performance needed some adjustment. We worsened it a bit to 15 picometers per root hertz, and that has to do with the fact that you always want to have some margins between the science, what science requires, and what the engineers will build, so that we are sure that we actually make the science requirements. We also had some organizational changes, and I think Martin Hewitson will tell you a little bit about maybe not the changes, but the current setup. Let's just say there were some iterations on the best way to manage the anticipated national contributions. That's quite normal in Europe. When you start things, you have some ideas, and then it turns out that there are possibly better ways or better streamlined ways of dealing with deliverables and interfaces and all that. And there has been a slight evolution of the payload concept. We haven't changed much, but there's a little bit about tilt to length compensation that has been changed. And there's a full session on that. It's the instrumentation session tomorrow evening at 8 o'clock. So if you're interested, go there, listen, and be amazed about how complicated things can become. Now that was 21. 22, earlier this year, we kicked off phase B1. And this might be a good time to tell you a little bit what those phases are. What does phase B mean in particular? Well, phase A that we just finished is the so-called mission feasibility phase. And that's all, you can read that. This is pretty much straight out of the standard. We have initial technical designs, but also importantly, assess the feasibility of things. Can we build the mission? Assess the risks. And phase B is the detailed design phase. And we typically split that up into two sub-phases, B1 and B2. We finalize plans, decide on hardware models, trade-off studies, develop design. And that's let's say the ideal case. But in LISA, some of our things are technically quite advanced. So maybe it isn't too relevant for LISA what these phases, what the clear or the ideal situation or ideal phasing there is. Let's put it that way. In phase A, we talked about the general concept and how to build a mission that delivers the maximum science and make people maximally happy. And here we are figuring out the details. And if you forgive me this flippant comment where, as I said, we make people maximally happy in phase A. From now on, we try to make people minimally unhappy because things will happen and it will impact poor performance certainly at some point. So, but we try to do the best we can. So, where does that lead to? In 2023, we are eyeing up to mission adoption, and then later on implementation and launch. So at adoption, phase B1 ends, and we proceed hopefully in phase B2. Now, why is this important? Because adoption is the point where the agency commits to the mission. And before I come to that, let me just tell you a little bit about where we are at the moment. In phase B1, we have contracts with 2 industrial companies, Airbus Defence and Space in Germany and Thales Alenia Aerospace in Italy. And we continued those contracts. They were already running in phase A and 4.5 million euro each. Just to give you a scale, the amount of money we already spent. We are asking them to run a few campaigns where they figure out who is able to build some hardware, the so-called request for information campaigns. And we also, on the study team, work more on the justification flow from the science requirements to the mission requirements, to system requirements. We don't want to have requirements that are not tied to any science requirements or science performance, because that would mean that we build a mission that is not really needed. And there's a long list of documents under preparation for the mission adoption review. I spare you the long list there. On the science side, maybe more interesting to this audience, we will have to provide the so-called Red Book, where the official name is Mission Definition Report. The science team is busy with working on the science parts in that document. It also will contain a mission description, a description of the mission architecture, the payload and all that. So that's a little bit more on the study team. Science requirements need to be updated and consolidated. It's not that there are big things missing, I think, that is fair to say, but we need to tie up some loose ends that were left dangling in the hectic for the proposal, so to speak. We know more about expected rates, expected signal to noise ratios, and make sure that we are displaying a solid case for that mission. And of course, these things need to be in sync. We don't want to say something in the Red Book that's not backed up by the science requirements and vice versa. So the science team and the study team, and particularly we on the study scientist side, Nora and myself and Ira Thorpe on the US side, are working hand in hand there. And there are also some, by the consortium, some additional studies underway and planned, impact of noise knowledge, impact of calibration knowledge, all these things we discovered during phase A that were not in the science requirement document yet. So what happens? We kicked off the contracts with the primes. We had already a couple of progress meetings by now. I think the most work is to work out the correct level and split of requirements there. There's a lot of work to be done on the schedule, and I come to that in a second, particularly on the assembly integration, verification, and testing, otherwise known as AIVT. Apologize for the acronyms there, because we have to build 3 spacecraft, and that takes time. And we want to minimize that time. The general work on overall spacecraft platform issues, it's kind of normal work. And this is now we are reaping the benefit of the somewhat longish heritage of LISA. The last review we went through effectively already considered that adequate. So we are a little bit beyond the status we should have at the end of phase A there. And that has simply to do with the fact that we are studying this mission since 20 years. On the instrument side, also work on requirement consolidation, work on implementation schedule, same story. We have to build 3 spacecraft. The instruments always come in triplicate or even more. We need to demonstrate some technologies. We need to put together the data packs for the instrument requirement reviews that come earlier than the mission adoption review. They lead into that. They start earlier next year, late this year already. And we also have to look into how we build engineering models after adoption. So adoption, the big word. November is currently planned for the November 23. And let me first tell you what it means. Adoption, as I already said, is a major milestone for ESA. And it means that we have the commitment by all stakeholders. That's a very nice managerial word. It means here ESA, the member states, and the international partners, in other words, NASA, to the respective contributions. We, ESA, will determine the cost to ESA, what we have to pay for that. And given the financial status of the agency, but not only of the agency, I mean, you look around in the world right now, economy isn't doing too well. You also will have noticed that ESA had a couple of programs jointly with Russia, namely ExoMars, and also we plan to launch the Euclid mission with the Soyuz. For quite obvious reasons, those plans had to be, let's say, revised, and that costs money. Plus, we are heading into a ministerial council at the end of the year. The ministerial council is the body that sets the general level of resources for the whole agency, but also for the science program. And given the current state of the world, it is prudent to assume that we are not getting a huge increase of funding. We might actually get no increase of the funding. So we have been asked by our Director of Science to keep it to within 1.3 billion. The current cost is slightly above that, not much, but a bit. But it still includes some margin that will go away at adoption. So we are not quite there yet, but we are working on it. Member states will sign up to a multilateral agreement where they say, we want to do this, whatever that is, instruments, data analysis, for example. And of course, we have effectively the commitment in hand, but it's not formal yet. Our international partners, that is NASA, they will enter a memorandum of understanding. Similar thing, just different names, specifying contributions. At the moment, NASA is willing to do some instruments, telescope, laser, charge management device for the GRS. There's strong indication that NASA will participate in the science ground segment. It is under discussion how we do that. Let me stress that adoption will happen when and if ready. So it's not that we say we adopt in November 23, it's a target date, but we will have to look at that and say, are we ready for adoption? This is 3 months earlier than expected. So this is the first time in my life, in my career, that I can stand up and say, we have a negative delay. It feels wonderful. On the other hand, it also feels scary because somebody just took 3 months out of our careful schedule. Now, the schedule is tight, but doable. Same for the cost. Now, you might ask, why did we advance 3 months? You will have heard, particularly if you have some ears in the X-ray community, that Athena is in a little bit of a financial and maybe also technical trouble. In other words, they are a little bit too expensive. They have been asked to come down from 1.9 billion also to the 1.2, 1.3 billion scale. And it's at the moment not considered a given that they will be ready with that for their original adoption date. So we have been asked to effectively jump forward a bit and fill that gap. The jury is still out there if this will actually happen, but we are planning for the November 23 event. So going on from there, we are starting then with phase B2 with the kickoff of the primes. You do some of the prime. By the way, this is why with the adoption, we end the parallel studies. It will be one company doing that. And then we go through different reviews. Now, mission PDR, preliminary design review, where phase B ends end 27, early 28. And then that leads us to the launch in the mid-2030s, 2035, 2036. This schedule is challenging. It also means that integration of the spacecraft has to be a bit streamlined. Testing needs to be streamlined, and we will have to make sure that we are not getting any holdups there. But, you know, we have to be a little bit optimistic in the planning. Now, also, who does what is also an interesting information for everybody. At the moment, ESA does the mission implementation, mission architect, space segment. You can read all that. NASA, as I already said, telescopes, laser system, charge management devices, and contribution to science exploitation, which is the science grant segment. And the member states and consortium instrument hardware, you can read it there, performance tests of and with the ground support equipment, science data processing, performance modeling and monitoring, and system support. So we have these three pillars to that mission: ESA, NASA, and the member states. Now, let me come to a close here and leave the floor to Martin and Linda, who have more interesting things to say. Let me put it like that. This is LISA's opportunity. It's the first time we went out of phase A into phase B1. Let's make it happen. So, as I said before, this also means that going from the regime where we try to make everybody as happy as possible, we will transition to the regime where we try hard to create as little unhappiness as possible. So with that, I would like to hand over to Martin Hewitson and try to stop sharing here.
Thank you, Oliver. I hope you can all hear me fine, and I will attempt to share the slides here. I have to start my video. I think my video was already on. Is that working fine?
It looks good.
Okay, thank you. Okay, so thank you very much, Oliver, and good morning also from my side to continue with this part of the presentation. I have to say it's a real pity we're not all meeting in person at one location, but at least I'm able to present from within a field of cabbages, which is not something you see every day. So I will try to cover the status of some of the activities on the consortium side. I won't touch on everything, but I will try to point to things as I go along that you will be able to look at throughout the week. And then I'll hand over to Linda to look at more details of the mission system level architecture and aspects. These days, it seems I can never make a presentation without having an organogram in it. So I'll start here just to give a sense of all the activities that are ongoing inside the consortium. And in particular, pointing to over on the left side here, Oliver alluded to this earlier about the organization changes we've done in phase A. This is partly to do with the way we're now setting up the hardware contributions from the member state side. You can see here we have 4 key subsystems that we're providing to the mission. We imagine in implementation there'll be a 5th added here, which will be our share of the ground segment. And then these activities are all integrated into the ESA top-down system engineering approach. You can see other aspects of the consortium here. There's a formulation management team which is supporting these activities and doing lots of system and mission level studies to support ESA. We have the LISA science group covering the utilization of all the science data we expect to get out of the mission. And we have the overall governance of a consortium of rather a large group of people, something like 1,500 or more people. What I'm actually going to talk about in a little bit more detail is some of the instrument key concepts and some of the components, and trying to give you a sense of who's providing what and where we are with those things. As I walk through this, I will say that all of the images are very notional. They're just sketched from my own modeling tool, and they're just for illustrative purposes, so they don't reflect any of the actual designs that the primes are doing. Oliver already told you that there are 2 competitive prime studies underway, and so we're not able to show in detail any of their designs. But if we look at the mission concept and start zooming in on where the places go, where the pieces from the consortium fit, we have 3 satellites, as you know, in LISA. We effectively exchange photons between these widely separated spacecraft to give us a probe of space-time, of proper time along that link. And in doing that, of course, we pick up noise of each of the spacecraft. So at the end of those arms, we have free-falling test masses, which act as quiet geodesic references against which we're able to reference the overall measurement along these links. It doesn't take you more than a second to realize that we have multiple links there between the 3 satellites, 6 in total, sending photons in each direction. Those then get combined in something that was already highlighted by Martin. It's in the agenda for this week in a number of places. We'll have Jean-Baptiste later this morning, in fact, going into detail. But we combine these 6 measurements together with some reference measurements to form effectively 3 quasi-independent Michelson-like combinations, so allowing us to do a lot of common mode rejection of things like frequency noise when we reform these data streams on the ground. So what goes into making up a spacecraft? The obvious things, we need a solar panel for power. In this case, we have micronewton thrusters to control something like a 2-ton spacecraft with micronewton precision. So this is at the kind of nanometer level of control. We have what we call MOSAs, moving optical subassemblies. These are the core of the laser instrument optical part, where we transmit and receive the light down the arms. I'll show you in a moment what's in there. And then we'll have a lot of electronics, key electronics to do the readout and to support all this measurement process. So within a MOSA, a moving optical subassembly, we have a telescope to receive and transmit light. We have an optical bench to form interferometry. We have a gravitational reference sensor at the back end here with a free-falling test mass to provide our geodesic reference, and then an overall mechanical structure to hold those elements together and to allow them to be pointed to cope with orbital mechanics and to cope with the fact that the spacecraft change their relative position in the sky with respect to each other over the course of a year. So there's a rotation axis through the back of the MOSA here through the test mass. So then looking deeper inside, we have a number of boxes, and I'm going to show you quite how many boxes we have in the end in a few slides. But we have front-end electronics for the readout of the test mass. We have phase meters to do the complex phase measurement. We have laser systems, and we have diagnostic systems as well. So there are lots of units to collect together from many partners across the consortium. These all need to be integrated. This is not meant, actually, this is meant to frighten everybody. There's a lot of pieces here. So just to go through some of the key ones, in order to form the optical bench assembly, and apologies for all the acronyms here, but it would make the slide too big. I have put a link to acronyms at the bottom, and I have put a little list to the side here. But we have a point-ahead angle mechanism, fiber switches, beam alignment mechanism, so that we have the photo receivers. We have a constellation acquisition sensor and power monitors. So there's lots of units that all have to be integrated on the optical bench, as well as key diagnostic sensors. Once we've got that, we can build it into a MOSA with the other elements. So that's a gravitational reference sensor head, which includes all the integration of the test mass and all the electrodes to do the readout and control. And again, diagnostics will all be integrated in there as well as on the telescope, and as well as on the MOSA itself. So this all forms now a MOSA. And then we take a MOSA and put a couple of those onto a spacecraft platform and combine it with many other units, the gravitational reference sensor electronics. We have the mechanism control units that we need for the GRS and for the optical bench. We have the diagnostic control unit, we have the lasers, we have the ultraviolet light source, and we have a frequency reference for the lasers. And I've tried to color code these so you see who's nominally providing these. We have the phase measurement system as well as part of the IDS mounted on the platform, and yet more diagnostics. And then once we've done that, we can pack those spacecraft into a rocket and launch those out to the required orbits. Now, that already looks like quite a lot. If you put the actual numbers on there of how many pieces that entails, it's many. So we don't have the exact numbers yet of all the diagnostic sensors, but if you just look at all the key large boxes here, large pieces of equipment that have to be delivered, integrated, tested, and so on, it's getting on for a couple of hundred pieces that have to come together on the timeline that Oliver already laid out, which is why the schedule is very much a critical aspect of all of this. So a little bit more detail of how the subsystem architecture is laid out. This is a scheme we've developed during phase A. We have the interferometric detection system, the gravitational reference system, and the science diagnostic system. I have a sketch here of how those units are related in terms of some of the key interfaces. The science diagnostic system gives us thermistors spread across the whole of the payload and the platform. as well as some heaters and magnetic coils and magnetometers on the platform. So that's a complex system that's spread out and has interfaces all over the place. We have the interferometric detection system, which is a well-bounded set of elements that allow us to do the interferometry and the phase measurement. And then we have the gravitational reference system, which brings together the key elements to allow us to do free-falling test masses. There are a number of talks about these. You'll see a couple of those spread over the next couple of days. So have a look for more information with those talks. Looking again at some of the key functions, I've mentioned these already. This is a slightly different view where you see how the units are connected in the Moser optically, and then there's a harnessing system that allows the units on the platform to connect together. For the optical metrology, we have key functions like sending and receiving the light through the telescope, forming the interferometry measurements on the optical bench, preparing the light that we actually use in all of that, and stabilizing it through the laser assembly, and then eventually reading out the optical beat signals and reading out the phases of those in the phase meter. And then on the gravitational reference sensor side, we have a free-falling test mass, of course, which has to be sensed and controlled within the GRS. We can do readout and actuation of that through the gravitational reference sensor electronics. And we can control the charge on the test mass, keeping it within spec using ultraviolet light. And all of these key functions are in place through some of the consortium provided items. All of that has to be tested, and this is an enormous effort. We're going to support this activity. The IDS, the Interferometric Detection System, has a key test campaign to be done fairly early in the program in order to secure a lot of the performance and a lot of the technology. France, the team at CNES and other labs within France are working to develop an environment for that, a facility to do this testing, and you'll hear about this from Hubert later. They're also developing test equipment to go one step further, which is to do some of the key testing we need to do at the Moser level. We can't do everything we need to do at the IDS level, and we can't do everything we need to do at that level at Moser level, but there's a split of test activities, and they need different complex equipment for each of those. So that's a major effort going on there as well. Putting some flags in place here. I've grouped these now in sort of pillars of products here, and who's leading them, who's developing, and who's providing which items. You can look at these flags offline. You see the four main pillars of the consortium hardware subsystems. You see we're also doing a lot of activity here, and I'll mention a couple of these in the next couple of slides to support the mission development and the mission formulation, performance operations, science ground segment, support to the engineering team on ESA side, and a lot of that coming out of the consortium experts. There are many, many talks. I've missed many of them off. I highlight a few here. Please go and have a look at the full program to see the talks on all of these different areas. I'll say something about performance. That's a key area we're working on. We've been developing a performance model since the very start of the phase A that Oliver was talking about. It's currently got something like 250 model elements in there that describe the system as we see it, the full constellation. We're working in B1 to map that system onto all of the requirements that are being held in all the various documents so that we can trace all of this. You can see that the overall model is split up into key technical domains, the test mass acceleration, the different interferometers, thermomechanical aspects, and then the post-processing residuals that we get doing the on-ground processing. So we're continuing to work on this through B1. We're also continuing to work on the tilt-to-length coupling that Oliver mentioned. This is a system-level concept that involves many actors. We developed that together with ESA and the primes during phase A, and we're continuing to do work on this, in particular in one key area, which is the aspect of doing the on-ground processing. We do a subtraction of this noise source on ground to recover the final part of the performance. And that requires developing techniques for that in order to know how well can we do that so that the system is built to support those activities. And you'll see a number of talks concentrated in one session later in the program. So let me just summarize. So our responsibilities on the consortium side and activities are pretty well defined now. We still have a little bit of work to do defining how we best do the mission support aspects during the implementation phase, which of the things we've been doing so far should continue. And we need to continue to work on the exact split of responsibilities on the science ground segment. We are quite advanced on this, but there's more work to be done talking to the partners. All of the hardware elements, however, have basically got an identified national provider now. We need to do some confirmation work over the next few months together with ESA and the member states themselves, the funding agencies, to make sure these responsibilities can be confirmed. We're also, and this is something I haven't talked about, but Oliver alluded to some of this when talking about the Red Book and so on. There's an enormous effort going on in the consortium from the LISA Science Group to support both the definition of the on-ground processing from ESA and CNES, but also to support the science study team in documenting what the mission's expected outcome will be in terms of this Red Book that Oliver talked about. And I'm sure you'll hear much more about the activities of the science group over the next few days. So I think from our side, all the key elements are in place. We can play our part in moving LISA past adoption. And I'll stop there and thank you and pass over to Linda for part 3 of our presentation.
Thank you, Martin. And Oliver, can I count on you to try and show my slides, please? I am the happy recipient of a new laptop under LISA 365, which is working, mostly being the keyword, unfortunately. Okay. Thank you ever so much, Oliver. Good morning or good and godly hour of the day, as the case may be. I'm Linda Mondin. I'm the LISA Study Payload Manager at ESA, and I will present the last part of the status update on LISA. And next slide, please, Oliver. Thank you ever so much. So essentially, what you see here is something which Oliver has already presented and heavily alluded to. And it showcases the different phases and tasks which are undertaken in the space project. I will not go on this, as you can find this first part on the Oliver slides. And Martin has also highlighted a few teeny tiny hurdles, which will give us plenty of white hair and wrinkles. So what I have undertaken to do is to have us dream a little of when LISA might come to see, finally, the interior of a fairing in space. So let's imagine our baby all grown up and ready to go on its first exciting trip. Change slide, please. Thank you. And so after having said goodbye to its launcher, each of the LISA spacecraft will be brought to a stable configuration. And we will check, while still in proximity with Earth, how they have weathered launch. We'll cross-check that we can activate, monitor, and verify all critical subsystems. And once we have that clean bill of health, we will start the transfer orbit acquisition maneuvers, and each of the LISA spacecraft, whatever we call them, will start its own trip towards its station. And the spacecraft will have, during this cruise phase, limited power, as the lion's share will be used by the electrical propulsion. Nonetheless, when the thrusters will be off, some power might be diverted to other activities, other than heating up the payload, and some science calibration or activities might be accessible. And it will take us about 500 days, having traveled 60 millions of kilometers away from the Earth, but remaining always at a very similar distance from the Sun, within 10% of 1 astronomical unit at all times. Each of these LISA spacecraft will reach its station and will be injected into their orbit. And next slide, please, Oliver. As you can see, the spacecraft will be placed into an heliocentric, Earth-trailing or Earth-leading orbit. You have the Earth trailing here. So it will be placed 20 degrees roughly away from the Earth along the orbit. And they will form at the corner of an equilateral triangle formation with an arm of 2.5 million kilometers. This constellation will turn cartwheels during its orbit. And the orbits have been selected such that stability of constellation for the planned mission lifetime of 10 years, 5 nominal plus 6 of extension, is guaranteed. Note, as you can see in the rightmost figure, that all orbits are closed. The main preliminary stability requirements are limiting the corner angle variations, as this forces us to have more optical MOSA tracking capabilities. Lomosa, which Martin has introduced you to. And this also, we need to limit the relative velocity to below 10 meters per second to cope with one bandwidth limitation of interferometric beam node detection from phase meter. And we also would like to keep arm length variations below 10%, and note that this constraint is never the limiting factor. The stability requirements can be achieved by maximizing the distance of information from Earth, and thus minimizing its gravitational impact. On the other hand, communication requirements place a limit on the maximum Earth distance, and we estimate currently that to be close to 65 million kilometers. Therefore, we set ourselves at 60 and let ourselves trade away. The trajectory plots you see on the lower parts of the graph showcase for the November launch date the transfer in the ecliptic frame on the left and the Earth or local orbital frame right. I am not an orbital expert, so if you have more questions, I'll refer you to the right person. Next slide, please. Okay, so we have now reached station, and we cross our fingers and hope not to die, because this is the time when one-shot mechanism will be activated. And some of these we might have potentially released earlier, such as a cage venting mechanism for the gravitational reference sensor. But this is not a given, it depends on many parameters. And once that activity, that hair-raising activity has been accomplished, each of the LISA spacecraft will start commissioning. First of all, we will cross-check any of the units on board the spacecraft functionally to start with, to verify the good health. Then we'll start cross-checking all performance indicators, and we will adjust parameters in order to make those performance indicators fit our understanding. The interface between ground and the space segment will also be checked, and it will be time to start the heavy lifting to build us a constellation. To start with, the laser links will have to be acquired. However, as any cat well knows, finding and catching the right laser spot is tricky business, and small adds might not be much of help. I will go into more detail in the following, but this is one of the main hurdles we think we are going to face. Once that is done, and with the spacecraft being kept under drag-free control around the test mass using 5 degrees of freedom electrostatic control, and the 6th from interferometric measurement by differential wavefront sensor, we will have also to adjust the point ahead angle, because this changes over time, and we need to adjust this in order to keep tracking the distant spacecraft. We will start ranging, and we'll cross-check that the laser link has the capability to transfer data, ranging information, clock correction information, and all of the spacecraft will come online. Then we will have to characterize the constellation, for example, tilt and end, as already mentioned, and time delay interferometry will be attempted for the very first time live. It will be possible to check the constellation responses to different perturbations we will inject in order to calibrate out the responses. So roughly 9 months after reaching station, the constellation will be born. Next slide, please. I said that acquiring the 6 or 3 bidirectional intersatellite laser links is not a trivial matter, and I stand by that. The spacecrafts are over 8 light seconds away, and even using state-of-the-art sub-trackers and precise computations, orbit restitution will be insufficient to pinpoint the position of a distant spacecraft in the vastness of space. Small field of view of the science detectors and the fact that detection will come only if the laser frequencies are no more than 25 megahertz apart makes the exercise a major challenge. The way out is to use a matricial detector, what we call the constellation acquisition system or sensor, but even so matters are far from pedestrian. Assuming that the spacecraft is commissioned, including characterization of a star tracker line of sight with respect to the constellation acquisition system, and that this constellation acquisition system can work while the spacecraft is also emitting light, an assumption which does hinge on transmit light backscatter management, a procedure identical for any arm, with some attitude constraints imposed as the arms are sufficiently acquired, is set in place. We are aiming to enable simultaneous acquisition, and we have done some studies internally in ESA in how to best to transition from straight tracker guidance to constellation acquisition sensor guidance, and finally to differential wavefront sensor. And I have a slide on this. Next slide, please. So first of all, we are looking at spacecraft 1 and spacecraft 3, and spacecraft 1 points outwards the laser towards where it thinks that spacecraft 2 is located. Then spacecraft 2 will do the same. It will take its star tracker input and will try to point towards where it thinks that spacecraft 1 is also located. And if you have an uncertainty cone, which is smaller than the field of view of its constellation acquisition sensor, at one point, while the spacecraft 1 will scan the angle of uncertainty, it will illuminate spacecraft 2. And as soon as spacecraft 2 has seen the light from the cast, it will salute to point its own laser back at spacecraft 1. And this is the maneuver you see done on the rightmost and bottom figure of the slide. Spacecraft 1, once it does see the light, which spacecraft 2 will have pointed back to it, will stop the scan and salute to point the laser to spacecraft 2. This is what you see in the leftmost bottom figure. This is the spacecraft doing that after scanning. After the stable cast detection, the spacecraft will switch to closed loop control and perform acquisition of all other arms under cast control. Finally, all transponder laser will be driven by the phase meter to perform frequency scans, and once the bit nodes have been acquired, the system will switch to the differential wavefront sensing control. Note that while acquisition of each arm can take up to 10 hours, no showstoppers were identified. And next slide, please. Okay, so after all these commissioning activities are completed, the real science begins. The aim is to provide the community with 4 years of data. And this drives a wish to minimize the interruptions. But some perturbations are inescapable. Maintenance operations such as mechanism actuations to keep the high gain antenna pointing towards the Earth, to correct the point ahead angle, as I mentioned, or the constellation briefing angle will have to be implemented. And the constellation frequency plan will have to be routinely updated. The test mass might need to be discharged, increasing noise. All of these are known knowns we can mitigate by, for example, downloading data to ground from a single spacecraft at the hub and reporting all antennas together. Nonetheless, there are also anomalies, and while some are known unknowns, like micrometeorites, next slide, please, we expect that there will be also unknown unknowns, as Donald Rasmussen reminds us. And this we'll discover only as we go. So we have predicted a certain number of safe modes without a cause, really, per year. And this seems like a safe assumptions, and we are doing our utmost to provide those 4 years of data. An extension of a science phase is accounted for, and all consumables are tailored to support those extra 6 years. The reliability, however, remains tailored for the nominal mission duration, as the cost of demonstrating reliability of an extended lifetime would be significant. Nonetheless, even now, a significant number of technology developments are running to ensure that the reliability of ELISA building blocks is as great as possible. And next slide, please. So one key technology for LISA are the cold gas thrusters that perform so satisfactorily for LISA Pathfinder. On the principle of not fixing what is not broken, the units should be reflights of LISA Pathfinder. However, there is obsolescence, and this on its own imposes some changes. And further, LISA Pathfinder was not representative to LISA, as, for example, LISA will require faster actuation and much increased lifetime. Thus, we have started an endurance test at Leonardo Florence premises, and we are happy to report that over 135 million cycles at 10 Hz and a further 317 million at 20 Hz have been accomplished, with no considerable evolution of key parameters such as capacitance, leakage, flow range, voltages, and other functional parameters. However, we did see a very small, slightly lowering of a plunger position, which is without consequences, but which we are trying to find the root cause of in order to make ourselves give us a warm, fuzzy feeling that this is not actually a failure waiting to happen. But so far, very much so good. Next slide, please. At NASA, we have the LISA development, which is progressing apace. In particular, the Micro Emperor has shown frequency stability is very close to the LISA requirements. The reliability of the units has been scrutinized and redundancies implemented to mitigate identified risks. The metrology ground support equipment has been developed and is under continuous optimization. iterations of magnetic Leibniz constraints allocation has been performed between ESA and NASA. A few challenges do remain. The RF noise, which does impact the clock noise correction in the 2 MHz frequency range, has been found to be higher than expected. NASA has launched a contract to understand the root causes of this phenomenon. And we have seen also a failure of a TRL4 unit on the test at the CSEM test house for ESA in Neuchâtel. The root cause identification is continuing, but if confirmed and affecting the electro-optical modulator, there are the redesign options which are certainly available, so we don't believe this to be an issue at all. Still, just for the sake of reporting everything we know now, this is it. And the message I want to give is that this unit is very much on track to demonstrate full TRL6 at adoption time frame, and more of this will be presented by Kenji on Wednesday around 16:20 CEST or thereabouts. Next slide, please. The NASA telescope development at L3 Harris Technologies is also progressing. The structural and thermal model is being assembled. You can see some very nice pictures, courtesy of L3 Harris Technologies. The first and the second optical demonstrators are manufactured, but the primary mirror of this EDU2 unit. And you can see the manufacturing of M1 at the bottommost, apologies, picture. And University of Florida's prepared facility and ground support equipment for characterization of a different demonstrator unit and is ready to go. Some challenges do remain to be addressed, such as the maximum temperature the unit can survive, which at 35 degrees Celsius, which I believe should be close to 95 Fahrenheit, raises some concerns as pertains to the criticality of temperature control, especially on the launch pad. Also, it has to be stressed that due to a tilt-length contributor identified by the Muller teams just prior to mission formulation review, the telescope design has had to be modified. Nonetheless, the current EDU program provides us with the confidence that a highly stable all-glass telescope can be built. The capability of such a design to withstand mechanical loads will be demonstrated in the coming months, and thus the telescope is well on track to demonstrate TRL6 for adoption. More will be presented by Jeff tomorrow around 16:15 CEST. And next slide, please. Slightly over time. So I'll just say that there are many, many more de-risking activities which we have undertaken. And I just would like to point out very happy news that after over 3 months into second laser-induced contamination long-term tests, we see no significant variation of key parameters such as transmission, wavefront quality, or polarization, which is very good news, as that has been a mission killer, or nearly so, for other missions, but seems not to be a huge issue for LISA. Fingers very much crossed that things keep going at least in that direction. I have another slide where I presented, next slide, please. Very quickly, some overall system engineering tasks which are advancing in the flow down from science requirement document to mission and the space segment requirements document. To report that interface requirements documents for all payload units have been issued in the first incarnation at the start of May, and we foresee a consolidated update at the end of the year in time for the instrument SRR at the start of 23. And IITV definition and schedule advances, as does identification of key concerns, such as cleanliness, with the help of a product assurance team at ESA. Next slide, please. In summary, as Oliver has already said, and Martin has reinforced, let's make LISA happen. Thanks all for your attention, and enjoy the following talks. That's all.
Thank you to all three of you. There is time for some questions. I would encourage people to ask questions through the Q&A of the webinar. We've had 1 or 2 questions posed that way. Actually, Oliver's been pretty fast and answered some of them. But we've had at least 1 question posed through the Oxford Instruments chat, and that's not the way that we would ask people to do it, because it requires us to keep our eyes on too many things at once. So if you can use the Q&A here, that would be ideal. I'm not sure whether everyone was watching it, but the 2 questions, one was really about an acronym issue, which Oliver answered about star trackers. The other one was slightly, more substantive in that it was asking about whether there was any preference of an Earth leading versus an Earth trailing orbit. And that was probably triggered by Linda's talk, and I'd invite her to comment. Oliver has said no, but there may be subtleties that you would like to comment on, Linda. Linda, you're muted.
Yes, of course, the main challenge of any web telecom. As I said, I'm not an expert on this subject matter. My understanding is that there is no clear preference. There are pros and cons to both, but they are ultimately largely irrelevant. It might just be which direction you turn cartwheels in, which has got more of an impact, and that is independent of whether you're trail leading or Earth leading.
Yeah, Linda, if I remember
Thank
correctly, what Waldemar said was Waldemar Martens is our orbit expert at ESOC in Darmstadt, and I think it has essentially which one of the two orbits is, let's say, energetically more favorable. In other words, you need less fuel to get there. Depends on effectively the season you're launching in, if you're launching summer or winter. Now the problem is I can't remember which one is which, so let's leave it there. It depends a little bit on the launch date, and otherwise it has no bearing on anything really. It takes the same time to get there. It does the same science. It doesn't help us or hinder us in any way.
Thank you.
I think Eric may have put a comment in the chat as well. I sort of saw it flying by.
Okay.
He knows better than I do.
If there is, I'll give some time for some other people to put any questions in the Q&A. But while we're doing that, I'm going to ask a provocative question, and it's probably addressed to all three of you. As we look towards potentially adoption in 23, what aspect of the whole mission readiness makes you feel most comfortable, and what aspect makes you feel least comfortable? Martin.
This is still recorded, is it?
Yeah,
it is
recording at this point.
It's going to go to posterity, so careful what we say.
I think one thing that makes me feel quite comfortable is that despite the fact that we've spent almost 4 years now well, actually it's a bit longer in phase 0, phase A, and part of B1, studying in depth the mission architecture as it was proposed, we haven't found any showstoppers, and the technology developments are well underway to convince ourselves of that. I think the flip side of that is, you asked what is maybe the least comfortable. On the other hand, I think that overall timeline and the number of units and the management of all of those things to make sure this all comes together on a timescale that we want it to is perhaps the most daunting aspect, but we're all well aware of it and are all working hard to make it happen.
Oliver, have you a comment?
Yeah, the only thing I can possibly comment on that one is, first of all, 3 months isn't exactly a huge amount of time. So it doesn't change things dramatically. However, it is to say we still have some technology activities that are locked in the schedule, where people are working and have looked at testing of things at a certain time, which now is a little bit behind from what we actually needed. But this is just also normal business in the sense of adoption needs to have a plausible demonstration that we have the right technology. And if the only thing that is late is that there's a test campaign still ongoing and may deliver results maybe 2 months after that review date, I don't think that this is a big issue. But clearly, we need to consolidate the schedule of the review with our Inspector General. This mission adoption review is a formal ESA review, which means it's conducted by our Inspector General. So there are if you like, this is kind of an internal external review, so it's not fully under control of the project. That would make no sense. So there needs to be some talking to the people and saying, look, this happens, and what do you need to be happy with our progress? And Martin Gehler, our study manager, who might be around already, is doing that. So I'm not overly worried there. At the moment, I'm more happy that we are finally accruing negative delay.
Thank you. Linda, do you have any final comment to add?
No, I think most of the points have been raised. I think it's a question of risk. Ultimately, we take a little more risks because some of those activities which we are using for technology demonstration will not be fully buckled up at the time of adoption. But most of those, luckily, will come sometime while adoption is still running. So we will know at least where we stand.
Thank you. That presents quite an uplifting picture, I think, for all of us to end this particular part of the programme on. Before we move to the coffee break, maybe I could just make one point about the posters and the pre-recorded talks. We've opened for each of them, and if you click on each of them in the Oxford Abstracts website, you'll find at the bottom of each of those elements a free-form text box where you can engage in comment or discussion about the content of the poster or the talk. And we would encourage those who are responsible for those presentations to keep their eye on that, and if questions are raised, to engage with the people who are asking the questions. You should also keep your eye on the Q&A, because I can see there are one or two things that have come in that we haven't had time to talk about, including comments on the orbit. And in particular, there's, I think, the comment that Graham Wone raised about solar co-rotating interaction regions. I think that's probably best posed to Waldemar, who's also responded in the Q&A to the Earth trailing versus Earth leading comment. So perhaps for some very specialist questions at that, the Q&A is a good way for people, the questioner and the potential expert, to make contact. So I think with that, we're just a couple of minutes ahead of time, which is always good at this point in the whole story. We will break until 1/4 the hour for coffee, and I would ask you to return promptly then, and we'll come back to hear from Monica about LISA signatures of massive black holes coalescences. So until 1/4 the hour, thank you, and we look forward to seeing you again shortly. Okay.
Thanks all. Bye-bye.
Hello, can I start sharing my presentation?
Hi, Monica.
Hi.
I'll just stop my share and you can take over.
Okay. Can you see my presentation?
Yes, looks good. But if you just hold on for another minute or so until we're ready, and then Harry will introduce you.
Yes. Harry,
Excellent.
I changed the title a bit, but I'm sorry.
It doesn't matter. That's all right. Can you go, Alex? Can we go? Well, welcome back, everybody. Just before we begin this part of the session, could I make just one comment? I mean, I think anyone who's signed in through Zoom has already, by definition, accepted that this is being recorded, but I just wanted to make it absolutely explicit that recording is happening. If anyone has any reservations about that, then of course they're at liberty to watch the YouTube stream instead. But those of you who've joined the Zoom have accepted that recording is in progress. So as we start this next part of the plenary, block 2 of the LISA Symposium 14, I would like to welcome, sorry, this is still block 1. I'd like to welcome Monica Colpi from Milan, who's going to tell us about the multi-messenger view of coalescing massive black holes. Monica, the floor is yours.
Harry, it is really a great pleasure to give this talk. It is an honor to be at this 14 symposium, LISA Symposium. Let me take you in this talk to distant galaxies where two massive black holes are embedded in a dense cloud. We see just the few orbits and we see plasma highly magnetized and shock heated that is being accreted. And now the newly formed black hole is recoiling and it's dragging with it bound material, bound gas. So from this nice GRMHD simulation by Federico Cattorini, it is clear that we expect to see electromagnetic radiation emerging during a coalescence event of two massive black holes. So they really join the vibration of space-time. But the key question I would like to address is detecting a counterpart a challenge? Let me first acknowledge a number of authors that have been contributing to this talk, from Silvia Bonoli to Alberto Cesana, and also my thanks to the writer and the coordinators, Joanna and Delphine, of the multi-messenger astrophysics chapter that is expected to appear in the Living Review of Relativity, which is a very nice introduction for those that are interested in entering this fascinating field. There is no doubt the science return of coincident gravitational wave and electromagnetic observation is immense. In physics, we can measure with exquisite accuracy the speed of gravity relative to the speed of light across cosmic distances. And in cosmology, we can measure the Hubble expansion, because massive black hole binaries are standard sirens, as you know, in that the gravitational wave signal is containing information on the luminosity distance. And if we detect a bright electromagnetic counterpart, if we identify the host galaxy, we can measure the redshift, and we can infer through gravity only the relationship between the luminosity distance and redshift to discover new physics about the dark energy and our expanding universe. In astrophysics, during the spiral, precursor emission, if detected, is going to tell us for the first time how accreting flows behaves in violently changing space-time. And at merger, coincident and or afterglow emission emerging now from a stationary horizon, the one from the newly formed recoiling black hole, will let us maybe witness the rebrightening of a disk or a launch of a jet. But what I believe is unique of the multi-messenger astrophysics with LISA is that our gravitational wave signal are sufficiently long-lived, say weeks or days during the spiral, so we can get information on the fly during the progress of the merger. So we can infer with some level of accuracy the shear mass, maybe the individual masses of the black holes, some information on the effective spin and about the luminosity distance. And these are precious information that can be provided to the astronomer to guide their search, select an optical UV or radio light curve, expect periodicity. And so just a selection of consistency will be extremely powerful in guiding us in the identification of the counterpart, together, of course, with the sky position. It is clear that the two universes has to talk to each other. And so with these two skies, we have to understand how large is the intersection between them. First, LISA, sky error uncertainty, has to be sufficiently small, let me say 10 square degrees or better fractions of a square degree, in order to match the field of view of an electromagnetic detector. And I am anticipating that this requires a selection of very loud signals, in particular if you want to detect the in-spiral. Second, the system sourcing the gravitational wave signal must be enough electromagnetically bright, because we are talking about relatively dim sources, to emit above the detection limit of the observatory and possibly be identified with an exposure time relatively short, less than a kilosecond. This again is very important if you want to follow the in-spiral phase. The electromagnetic source preferentially should display also smoking gun signatures in the spectrum or in the light curve, so we could unambiguously identify the true standard sirens among the many AGN that are in the LISA sky. No transient active galactic nuclei emission has ever been observed that could be attributed to a LISA coalescence event consumed over a time scale of weeks, days, or hours. We don't have, let's say, a scaled up GRB counterpart. And also little is known about accreting black holes of masses between 10 to the 5 and 10 to the 7 solar masses, for which LISA is most sensitive. We don't know how well we can apply the bolometric corrections that has been studied for the bright AGN. We don't know whether the spectra are different from the bright AGN. As well, we don't know the intrinsic variability even of single individual massive black holes, nor the level of obscuration associated to a merger event. So the feasibility of a multi-messenger discovery relies on one side on theoretical modeling and on the other side on simulating observational strategies. So let's imagine you have two black holes, LISA black holes, embedded in a circumbinary disk, say weeks before merging, so the fluid flow is still somewhat stationary. We know that the binary is going to excavate a cavity because of the interplay between the gravitational torque of the binary, which is trying to transport angular momentum away into the disk, and the viscous torques that are present in the disk. But it has been shown by many authors that in reality, the cavity is not empty, but it contains tenuous gas. And in addition, there is a sort of natural development of a nonlinear m=1 asymmetry in the density field called lump that is feeding in sequence two mini disks. So accretion can occur down to the horizons of the two black holes, and periodicities commensurate to the fluid patterns could be really clear signature. So bit frequency between the orbital frequency of the lump and the orbital frequency of the binary, which are longer than the orbital period. As far as the spectral energy distribution, average spectral energy distribution is concerned, in this plot you see nu L nu, which is providing the luminosity integrated per redshift bin, per energy bin, and you see that there is a prominent UV peak resulting from the multi-black body colored emission from the inner rim of the circumbinary disk, plus the contribution, so this area, plus the contribution of the two mini disks. But if there is a corona and a very hot electrons, then we expect to see a prominent amp at X-ray energy, say between 1 keV and even several tens of a keV, due to inverse Compton scattering of the soft photon by the ultra-relativistic electrons. Let me just mention one nice finding recent by Pascalidi et al. So here you see in these view graphs the two mini disks, and what has been found is that these mini disks are brighter if the black holes are spinning along the orbital angular momentum axis and dimmer in the opposite case, simply because the innermost stable orbit here, the white circle, is closer to the horizon if the black holes are spinning fast and in the direction of the orbit. And the extension of the disk is mainly truncated by the Hill sphere, that is, they cannot extend further because of the tidal field of the companion, which is disrupting otherwise the structure. LISA binaries with electromagnetic counterparts are likely to be already on years, centuries before coalescence, maybe before I was born. But you can clearly see that the erosion of the extension of the mini disk as they come closer and closer and closer implies that there might be a dimming in the X-ray luminosity during the spiral, and this could be a signature of the pre-merger emission. We might still observe periodicities. For instance, in our simulation, we see a periodicity in the accretion rate, which is going hand in hand with the shear. But then we have also to consider the merger. the rebrightening of the disk. Depending on whether the kick, the recoil, is in plane, which means that the spins initially before the merger are parallel to the orbital angular momentum, as it is expected, especially in a merger which is driven by a circumbinary disk, then the black hole is piercing down into the disk, creating shocks that could be revealed. The luminosities of these shocks, as been shown, are not very intense, over the level of 10 to the 42 x per second, but this is a very interesting possibility for detecting light. If the kick is perpendicular, then the black hole is dragging the bound disk, but since there is an ingent mass loss, because 10% of the mass rest energy has been released in gravitational waves, the orbits inside the disk become elliptical and also are less bound. And this again is causing features in the disk and shocks that can make the disk rebrightening. If there is a magnetized jet, as observed in many cases, then you would expect to see either a prompt or afterglow emission. In the interaction of the jet that has been accelerated with the wind bubble that is associated to the large-scale circumbinary disk. Yuan et al. Has demonstrated that time delays can be of days to months when we scale the gamma ray process from a 10 solar mass black hole to a 1,000,000 solar mass black hole. The spectrum is broad range from radios to gamma rays energies. So we know that the spectrum is broadband. It could come in radio, UV, and X-rays. But how well can LISA localize a source? So first with Alberto Mangiali and recently with Sylvain Marsat, we consider to study 3 families of binaries. Binaries with total mass 3 times 10 to the 5 solar masses, light binaries, intermediate binaries of 3 times 10 to the 6, and heavy binaries of mass 10 to the 7. These are not single binaries, but it is a family of binaries because we let the mass ratio to vary between 0.1 and 1, and also we accounted for the presence of aligned spin. The parameter estimation has been carried on using higher order harmonics, both in spiral merger and ring down with 3, 3, and 4, 4, that we know are relevant when the mass, when the binaries do not have different masses. And we know that in particular, these higher order harmonics are breaking degeneracies and are very, very important at the time of merger. Here you see the SNR as a function of the time to merger for these 3 families. And what you should notice immediately is first that for the light binaries, these are only detected as soon a month before they merge. The intermediate one, a week. The heavy one can be detected only 3 days in advance. As expected, the SNR is increasing, but notice again that it is increasing by 2 orders of magnitude, and the SNR is extraordinarily loud, 10 to the 3 solar mass, 10 to the 3. And at merger, these are very, very loud sources, the one that we are going to use to test gravity. But despite being so loud, what is the sky position uncertainties for these binaries that are placed at redshift 1? Here I'm plotting delta omega versus against the time to coalescence. And you immediately see that for the 3 families at the very beginning of their detection, they are almost you can't place them in any position in the sky. For the light binaries, there is an improvement, a narrowing of delta omega by exploiting the Lisa motion, but notice that it stays almost constant until the merger is occurring, where the higher order modes can help in disentangling various degeneracies. And also you can also notice that for these systems, they enter the Vera-Rubin LSST field of view only at merger, and for a fraction, particularly for the intermediate mass binary, more than a half of these binaries could be detected by Athena having a field of view of 0.4 degrees. So the mergers seem to be somewhat guaranteed, but what about the possibility of also tracing the in-spiral phase, which is so nicely associated to the features that we have, I have shown previously. So if you take a light binary of 3 × 10⁵ solar masses at redshift 0.3, so really very nearby, almost as soon as it is detected above an SNR of 10, the binary is entering the LSST field of view. And instead, Athena, and for a fraction of these binaries, can detect, can localize the source, just say 1 day before merging. Please notice these light lines are trajectories of individual binaries varying the mass ratio. Since we know that the slew time of Athena in the configuration that has been presented for the selection, the slew time of Athena is 4 hours, and Matteo Guagnazzi has computed that tiling the LSST field of view, you can make it so you can cover 10 square degrees with Athena in 3 days by performing at least 23 observations lasting each 9 kiloseconds. And this 9 kiloseconds is dictated by the fact that I need to have time to detect the source above the confusion limit. So in order to detect 2 points in the light curve before merger, alerts has to be sent 6 days in advance, but we have detected the binary 10 days earlier. So if we know also the shear mass and the mass ratio with high accuracy, then we can alert our friends, and they can then select light curve for a better following of the source. As far as sky multimodality is concerned, Sylvain Marsat has shown that there is degeneracy in the signal, and bimodality can remain until the merger. For these platinum binaries at very close redshift, we see that we can just spot a single area in the sky and stare there even 8 days before, because there is no sky multimodality. But for the most distant binaries, this can really hamper the sky localization, because you don't know where to point your telescope. But in a paper that has been submitted today by Alberto Mangiagli, it seems that by looking at the posterior distribution of these binaries, they only represent a minority of the cases. And so they do not affect much the number of expected electromagnetic counterparts at mergers. But how many galaxies are in the LISA sky error boxes? before and after the merger. How many AGN are in the Lisa error box? AGNs that are false positive, there is only one, which is the true source. So we decided to attack this problem by just simulating a universe, our mock universe on one side, and on the other side to study the response by Athena and Lynx. And also we have considered a sort of shallower observatory having a lower imaging resolution. And here is our simulated universe that we constructed using a semi-analytical model called Galaxies, constructed by Davide Izquierdo and Silvia Bonoli on top of the Millennium simulation. And clearly you see here the light cone extending up to redshift 3, and you can appreciate the beauty of the galaxy filaments that we can see in our cosmic web, because the Millennium is providing the dark matter halo mass distribution and their position in redshift. But in our mock universe, we know every single properties of the galaxies that are present. So we know which binary are hosted, and also we treated the dynamics during the hardening phase through stars and gases. So it is a universe which is containing really a lot of information. Here you see the projection of this light cone in declination and right accession is covering almost 1000 square degrees, and these little rectangle are just the sky localization uncertainty of Lisa for these two sources that we have selected in our study. And here you see the projection in the plane redshift versus right ascension. You can see in this red and blue dot the distribution of the filament and the galaxies that are surrounding our binaries. Let me just give you one example. Suppose you have a binary with total mass of a few million degrees at redshift 2. It is almost in the Athena field of view, and it is well spotted by LSST. The true source is the red dot, and you see that it is surrounded by more than 10 to the 3, but I would say 10 to the 4 galaxies. So it is extremely difficult to make an association of the true host being embedded in a sea of galaxies. But instead, if you consider a lighter binary of 3 times 10 to the 5 at redshift 0.5, what you see that there are only 100 galaxies within also the Athena field of view. And also with LSST, you can sort of monitor easily the light curves. So there is a really major change in our ability of comparing the galaxy counterparts in these two fields. But if you then decide that you are looking only at the X-ray sky, our binaries are emitting at the Eddington limit. We have included all bolometric corrections, so we can calculate the flux expected in the Athena wide field instrument. And we see that there are about 70 active galactic nuclei that are brighter than our true source. And there is just one single AGN detected by eRosita, the survey, the whole sky survey, which is shallower, but it is providing more than 1 million AGN over the whole sky. But if we can explore even dimmer AGN, now the number, even at high redshift and at merger, reduces significantly, and with several hours of exposure times in the soft, we can detect the true counterpart. It is clear from the bottom panel instead that when the source is so nearby, you see only few AGN around, just one. This is statistically affected, but the right, given that our sources are very dim compared to the bright quasar, and with a sufficiently small exposure time, we can just spot the X-ray source. So we investigated the parameter space, and let me just tell you in a nutshell that X-ray selection of counterparts is key to reduce the number of potential host candidates and help identifying the source, which is an X-ray source. At merger, the typical number of AGN is 100, except for the very light binary, which is only a handful. We studied obscuration, which requires longer exposure times to detect the source, only in the hard X-rays. But if you stare at merger, we can go back and forth and observe the source in different times for a sufficiently long time. Reducing the reduction of the imaging resolution prevent any detection of counterparts, because their fluxes are below the confusion limit, and LINX is far more rapid in detecting the electromagnetic source, but of course, having a field of view of 0.1 square degrees, it requires large number of pointings. If we want to trace the spiral, send alert, let us look at nearby light binaries. I have just 2 minutes more. If we have a dual network, as shown in a paper by Schumann and Cornish, sky localization decrease by 3 orders of magnitudes in the best, most favorable configuration. The luminosity distance uncertainty reduces by 1 order of magnitude. We are just limited by weak lensing. And at merger, the number of AGN we computed is just a few. You just spot the true counterpart, and tracing the spiral require far less number of pointings. As far as rate are concerned, this has been computed by the paper that appeared today together with the paper on our simulated universe on arXiv for feedback. So Alberto has computed the rate, the number of expected electromagnetic counterparts in 4 years of operation of joint observation in the X-ray, optical and radio telescopes. And if you include obscuration, this number goes to 2 to 3. These are the rate at merger. As far as morphology is concerned, in our mock universe, you have seen that the AGN that are the false positive in our LISA sky are normally placed in crowded areas because they are more massive. But the true LISA sources has to be looked for in low density regions where dwarf galaxies are, which are hosting our light black holes. And if you have to look at the morphology, please don't look at a disturbed galaxy, morphologically speaking, because by the time the merger of the galaxies has occurred and the time the merger of the 2 black holes has occurred, the galaxies have time to relax. Maybe next, I will leave it. I want to close, and I think I have convinced that it is a challenge, but it is a great challenge that we have to pursue. And it is a difficult challenge, and the reason is very, very simple. I think that many of you recognize one of the greatest Karsten slide when we submitted LISA to the attention of ESA. This you recognize is the waterfall plot showing that LISA is going to explore a complementary space, complementary masses compared to electromagnetic observation. But the joint observation really are confined in a sort of a narrow intersection, and this is why It is a challenge, but we will make it. Thanks a lot.
Thank you, Monica. Thank you for that beautiful exposition, and one which makes the case, I think, very cogently for the importance also of an X-ray mission coexisting with LISA, and that's something that the LISA community certainly strongly supports and endorses. We have one or two questions in the Q&A, and one of them takes you back, Monica, to your localization slides. If you could go back to that, and it's a question about why there was a break between the shaded curves before and after the 1 hour point. I think it was probably just a gap.
No, it's just the way you represent it. You have to represent the merger, but the signal is continuous. It was just because the scale is not adequate to represent this gap.
That's what I supposed. Another question is, how long does it take to identify a source once it enters the LSST field of view? Is that a quick process?
For the LSST, depending on the magnitude, LSST has a limiting magnitude of 24.5. It might be not so difficult, but the point is that if you have so many galaxies, you don't know where to look at, and so you need to have a field of view for LSST, which is again very poor of galaxies in order to detect any change in the spectrum. As far as Athena is concerned, this is a very delicate issue. You have to introduce the bolometric corrections, and if you need several pointings, that has to be done over a time scale which is shorter than the merger. You see mostly the merger and so the spiral for very nearby sources. Otherwise, you can't make it. There is a nice table in our paper on that.
Thanks. Now, there's a tricky question from Stefano Vitali. If Athena, and it's an if, has to descope something, what would you keep? What aspect of its performance would you keep at all costs to guarantee the best synergy with LISA?
This is a very provocative question, Stefano. Well, we need a wide field instrument, of course, but we have verified that if the imaging sensitivity is, the imaging capabilities are around 10 arcsecond, you lose the spiral and almost most of the sources, because when you don't have much spatial resolution, the risk is that your sources are below the confusion limit, so they cannot be distinguished by the X-ray background. So I would need the WF5 making the very strong effort to keep an imaging resolution at the 5 arcsecond that has been proposed during the design. The XIFU is a different issue, because the XIFU was conceived to study galaxy clusters, okay, and so do spectroscopy. And XIFU here can be used maybe in the sources that can be detected within the arc-minute field of view of the XIFU. But we need a wide field instrument, so drop the XIFU, but I'm sure that some people in the Athena team would completely disagree, because it depends on really whether you would like to see the hot universe or the energetic universe.
Thank you for that politic reply. There's one final question on, there's a comment from Stefano that it was a great talk. I think we would endorse that. But before we finish, there's one final question from Shan Chen, which is a question of what would happen if a merger took place in a gas-poor galaxy so that there was no perceptible X-ray emission. Is there anything that we can do about localization then from any other part of the EM spectrum or not?
Well, localization is sort of independent on what is its electromagnetic counterpart. And so localization is there. So if you know that it is in a dry merger galaxy, I would say that maybe since you can still launch a jet, let's look in the radio or in the very high gamma rays to see whether you can still see some radio emission, but it is very difficult. In the simulation we did with Federico Cattorini, which are very idealized and the gas is tenuous, we didn't had time to make ray tracing, but the emission reminds me the old days when we were studying the X-ray emission from spherical accretion. And but if it is magnetized, maybe some signal is there. The point I would like to make is that, and that has been made in the paper by Elena Rossi as well as in this one, and that needs urgent analysis, is how much time do we have to wait once we know exactly the time of merger in order to see the appearance of something, even in a gas-rich merger. Because it is week or months, then we could sort of associate a particular feature to a source. But if it is a year, the variability of active galactic nuclei is such so that we have really to be Sherlock Holmes and try to really look at the finest detail. And so I hope that by the time Lisa will fly, we will have a repository of light curves from simulations that can maybe post-merger, which are very difficult because they require a lot of time. So even analytical estimates to address this issue.
Well, thank you again on behalf of all the listeners for an excellent talk, Monica. Thank you very much.
Thank you, and thanks again for the kind invitation.
So we move now to the final talk in this section, which is going to be a talk on TDI, time delay interferometry, which is a critical component of the LISA mission. And this will be given by Jean-Baptiste Bayle, currently at the University of Glasgow, but until recently based at JPL. So I'll pass over to Jean-Baptiste.
Hi, Harry. Thank you very much. I'm going to start sharing my screen. Hopefully you're going to see the slides. Do you?
Yes, that's fine.
Awesome. Well, thank you very much. And thanks a lot for giving me the opportunity to talk here. It's a real pleasure to be at this symposium and present a little bit of context and a little bit of new results about time delay interferometry. So I'm going to start right ahead with what's on the menu for today. I'm going to start to give a brief historical overview of TDI, the main motivations behind TDI, and the first proposals. Then I'm going to move about the baseline for LISA, so what we plan to implement as part of TDI. And then I'm going to open this presentation with more recent studies and results. There are going to be a lot of references to talks that will be given during the symposium, so hopefully it's a good stepping stone to other more complete and in detail talks of the various things related to TDI. Okay, so let's start with a brief historical overview, and before everything, a few disclaimers. So this part is largely inspired from the excellent living review from Massimo Tinto about time delay interferometry. And a second one, important one, is I apologize if there are any errors or omissions in there. This is a large field with a lot of different papers, and I might have forgotten some of them or forgotten some names, so I'm really sorry if I did. And I'm not trying to find myself excuses, but also the story begins when I was only a little boy and I couldn't talk at that time. So, you know, that also I'm trying to keep up and make up for the time I didn't really experience. That being said, I will try to do my best to be as clear as possible. All right, so let's start with the beginning and talk about equal arm interferometers. So just like Virgo and LIGO that you all know about, laser light is affected by intrinsic frequency instabilities that we will call laser noise in this talk. But the good thing is that in an equal arm interferometer, because both arms experience the same delay, when both lights recombine at the photoreceiver, laser noise actually cancel out. And you can see it with a very simple view of it. You have here an equal arm interferometer with perpendicular arms of length L, which is here expressed in seconds. And so if you write the phase of the photoreceiver, you have basically the laser noise P taken at 2 different times, delayed actually by the same delay. So you end up with them taken at the same time, and therefore laser noise cancels. And that's why we can actually measure gravitational waves of strain of the order of -10 to the -20 with laser sources that are only stable at the order of 10 to the -13. Unfortunately, LISA flies, and the LISA constellation is breathing due to orbital mechanics. And therefore, we cannot really have an equal arm interferometer, and we have to deal with these unequal arms. As a reference, I just put here the expected light travel time, so in seconds, between the different arms, between the different spacecraft of LISA. And as you can see, it varies quite a lot over the mission by around 5%. And the same computation as we did before, but with unequal arms, shows that laser noise does not cancel at the photoreceiver. And we can very quickly estimate the power at the photoreceiver due to laser noise by just going to the frequency domain. And we have something that's proportional to the arm length mismatch squared times the laser noise PSD. And so if I just put in some numbers at 1 millihertz for an arm mismatch of around 0.2 seconds, which is what we will have for LISA, one finds a laser noise of the order of 10 to the -15 in terms of strain, so well above the 10 to the -20 that we wish to attain. And this is just a very quick simulation to show you if you have a laser noise at 10 to a white laser noise at 10 to the -13 for different mismatches. You have a residual laser noise at the photoreceiver well above these 10 to the -20. And so the original idea dates back to quite a long time ago. And the idea is that we can measure, actually, we can perform 2 interferometric measurements, one on each of the 2 arms, as seen here. So basically, you compare the light that has traveled back and forth on one arm and the light that's directly from the laser source. And so you have 2 measurements, Y1 and Y2. You can write here their expressions. So Y1 is just the laser noise delayed by twice the arm length L1 minus just the laser noise taken at P. And Y2 is the same, but with L2. And so going to the frequency domain, you can see that you have a certain transfer function for the laser noise. And I added here the gravitational wave signals as well. And so the idea is that you can divide both of these measurements by the laser noise transfer function, which is here given as exponentials, -1, and combine them with a minus sign such that laser noise actually cancels, and you get a quantity which is only dependent on here the gravitational wave signal, of course modulated. So that works, but the problem is that you have to account for the fact that the data that you get have a finite duration, so you have a windowing effect. And in a paper from 1990, Tinto et al. Showed that you actually need to integrate this signal for 6 months to get the suppression that you need. So based on the same setup, they proposed an alternative, which is which can work in the time domain, which is, in this very simple example, you can take y1 minus y2, you write the expression, and you can also delay in post-processing y1 by twice the arm length 2, and y2 by twice the arm length 1. And what you find is that you get exactly the same expression. So by subtracting them both, so you do y1 minus y2 and y1 delayed minus y2 delayed, you can form, again, in the time domain this time, a laser noise-free quantity that's identified to a Michelson interferometric measurements. There's another slight complication here, is that here we've considered that we have actually an arm where light is sent, reflected on a mirror, and then sent back so that it recombines in the end. So here is a simple optical schematics of this single transponder arm. But in LISA, it's actually not possible because we have arm length of more than 1 million kilometers. So that if you start with laser sources of a few watts, in the end, what you receive on the other side at the mirror, you received only tens of picowatts. So of course, there is no way that light can be reflected back, so that we have to send a fresh laser beam containing independent laser noise. So let us see if we can actually reproduce, by combining the data, just like we did before, this responder arm. So the responder arm, just as a reminder, we want some data y, which contains the laser noise delay by twice the arm length minus the laser noise at time t. And we can actually do that. We can synthesize this transponder arm using this setup. So again, you have this red laser noise, which is a one-way measurement. And on the other side, you have another independent laser noise, laser source, a yellow one, P2, which is a one-way measurement as well. And what we do is we perform 2 measurements at each side, mixing both the red and the yellow laser noises. And so Y1 is basically the distant yellow laser noise delayed minus the local one, and vice versa for Y2. And actually, a very simple combination, if you delay Y2 by the light travel time and you subtract y1, you can actually show that you recover the transponder measurements. So you've canceled out this yellow laser noise. And so by doing that, we've basically recovered the previous situation. So basically, we've demonstrated with very simple toy model examples, hand-wavy methods that we can reconstruct the standard equal arm Michelson variables by just applying time shifts to the interferometric measurements and linearly combining them. Tinto, Durandar, Nayak, and Vinay actually proposed a systematic method based on an algebraic formalism in 2002 to find these combinations. So in the same kind of setup where the arm length are constant in time but unequal, you can associate basically to each of the 6 interferometric measurements that you can do. You remember, 1 at each of the sides of each link. You can associate a polynomial of delay operators. The delays are just operators that time shift the data by the arm length. And you can show that mathematically, those delay polynomials, they form a mathematical ring. So it's not a field. So basically, the solutions that you're looking for are part of a module, not a vector space, so it's slightly more complicated. And in the end, we look for all the 6 tuples of these delay polynomials that can cancel laser noise. Assuming the static constellation, we can actually find that the entire TDI space is a free submodule that can be generated by 4 combinations. So just knowing 4 of these combinations, you can generate the entire set. And usually these generators are given as the Sagnac combinations, alpha, beta, gamma, and this zeta. There's a nice geometrical interpretation for these combinations, and especially the first 3 Sagnac combinations. If you write what alpha looks like, so it looks something like this. So I'm using the conventions, these double indices conventions. So on the right side of the slide, you can see that I label the spacecraft 1, 2, and 3. And as you know, on board each of the spacecraft, you have 2 MOSAs, and we just index them with 2 numbers. The first one is the number of the spacecraft it is hosted on, it is mounted on, and the second one is the index of the spacecraft it looks at. And I write all the interferometric measurements using the same kind of indices. And so alpha is basically given by a bunch of linear combinations of these y's, these interferometric measurements, on which we apply the delay operators. Here, for example, you have y12 without any delay plus y23, so something measured on MOSA 23, delayed by 1, 2. 1, 2 is just the arm length between 1 and 2. And so if you look at what it means really, it means that you started with measurements at MOSA 1, 2, and then you used the measurements at MOSA 2, 3, which you delayed by 1, 2. So you go back to spacecraft 1. And you do the same with the measurements y31 measured on spacecraft 3, on which you apply the delays going from spacecraft 3 to 2 and then 2 to 1. So basically you've done some kind of a loop. And if you look at the second expression with the minus signs, you basically have the same thing on the other side. So a nice interpretation is to say that you have reconstructed virtual beams that travel through the constellation on one direction, and then that interferes with another one that goes on the other direction. And actually, it can be shown that there are actually a lot of different laser noise canceling combinations. And some of them, unlike the Sagnac combinations, only use 4 of the links. So that can be useful in case of a link failure. You probably have heard about the Michelson one, XYZ, but there are a couple of them, other ones that have also some kind of geometric interpretation, as you can see here on the right. You have the beacon combinations, the monitor, and the relay. Of course, all of them are generated by the 4 generators that I mentioned before. All right, so there are a lot of combinations, and of course, each of them has a different noise transfer function and a different signal transfer function. And in 2002, Prince et al. Showed that if you assume a static equal arm constellation with unequal readout and test mass noises, which are the dominant noises after you removed laser noise, you can find 3 combinations that have a diagonal covariance matrix and whose sky average sensitivity is optimal. Usually we call them the orthogonal combinations, and these are denoted A, E, and T. These are the ones that are used for parameter estimation and data analysis. So that was an important step. And in 2003, Nayak and al. Showed actually that if you know the location, the sky location of your source, you can actually opt in for specific combinations that are optimal for this location in the sky. And so that leads to the idea of coherent source tracking by switching the combination if you want to follow one particular source or one particular location in the sky as the constellation moves. All right, so that was it for the brief historical overview. Now I'm going to go a little bit more in detail about what we plan for the LISA mission itself. So in LISA, the situation is, again, slightly more complex. As you know, we have 2 laser sources by spacecraft for each of the spacecraft, and we perform actually multiple measurements on each of the MOSAs. We have 3 interferometers. We have the inner spacecraft interferometers that monitors the spacecraft to spacecraft distance, and this is where your gravitational wave signals appear. You have the test mass interferometers that monitor the spacecraft to test mass distance. And of course, the idea is that you can combine these ISI and test mass interferometers together to rebuild the test mass to test mass distances. And lastly, you have the reference interferometer that just compares the 2 adjacent lasers. So the hope is to reduce the problem to the 3 independent lasers that we had before on the original TDI concepts. And so in the end, what we plan is a multi-step algorithm, TDI algorithm, that was first proposed by Estabrook, Tinto, and Armstrong, based on the same algebraic formalism, where we have intermediary combinations used to reduce the problem, the more complex problem of LISA, to the previous problem, where you have only 3 independent lasers and only one interferometric measurements per MOSA. And all of that feeds the usual laser noise suppressing combinations as the Michelson combinations or the orthogonal combinations. And this is what I tried to represent here on the bottom of the screen, where you start by suppressing the spacecraft motion. So you rebuild the test mass to test mass distance. Then you reduce to 3 independent lasers using these eta combinations, and then you can proceed with your usual Michelson or whatnot combinations. Just a note, in the larger context of LISA, TDI is only one of the steps that we need to prepare the data before gravitational wave searches and parameter estimation. This is what's called the INREP, or initial noise reduction pipeline. This is everything going from L0.5 and L1. And here we have, for example, the need to suppress other noises, to perform some calibrations, to estimate the light travel times before it can be used by TDI, or to resynchronize the data to a single time frame. So keep in mind that TDI is only one of the steps of INREP. Okay, one last problem for LISA. In everything that we've said so far, we've assumed that the constellation is static. That means that the arm length are constant in time. And this is actually not true, as we said before, because the LISA constellation is breathing. The arm length are expected to vary over the mission, and we actually have a relative velocity of the spacecraft along the lines of sight of about 10 meters per second. So that's quite important. And of course, that breaks the previous assumptions. For example, the delays that we use, the delay operators, now commute. Another consequence is that the delays, the arm length, or the light travel times from spacecraft I to J is not anymore equal to the same light travel time from J to I. So as a consequence, the traditional combinations that we've presented before do not cancel laser noise exactly. And taking a closer look, we can see that actually using the traditional combinations, laser noise residual, so what's left after, remains an order of magnitude above the requirements. And so this is a quick simulation that I've done just to show you with LISA instrument, so a simulation tool. The curve that you have on the top, the blue one, represents the raw measurements. So for example, the inner spacecraft measurements with only laser noise here. The red curve represents the noise allocation, so the requirements that we have on noises. That means that laser noise should be below this. And if you apply the usual TDI Michelson first generation, so the one that we've presented so far, with realistic orbits, you get the orange curve, which of course lies above the requirements. So we need to find a solution for that. And Tinto, Estabrook, and Armstrong in 2002 proposed a recursive method to find new combinations based on the previous one, the existing ones, but accounting for the breathing of the constellation to first order. Usually we call these combinations the second generation combinations. And so they account for unequal time varying arm length. They can have a geometrical interpretation as well. So for example, if I take the Michelson X combination, but of second generation, I just sense all the spacecraft again, so a second time. So you go around the constellation the second time. And this is what's shown on the right-hand side here. The first generation is going from 1 to 3, back to 1, to 2, and then back to 1 only once, and interfere with another virtual beam that goes in the other direction. But the second generation counterpart does that twice. So you go from 1 to 3, back to 1 to 2 to 1, and then you go on the other direction for the first beam, and then you redo everything for the second beam. One of the issues is that when you have your ring that do not commute, as we said, now because the arm length are time varying, the delay operators do not commute, then we couldn't find a finite set of generators. That means that we actually don't really know how to define the entire TDI space for second generation combinations. Of course, next generation, so third generation combinations and so on can also be found, but it's been shown that second generation is sufficient, as you can see on the graph, which is exactly similar to the one of the previous slide, but I computed the second generation TDI Michelson, and as you can see, it's well below the requirements in red. Okay, so that's the view of what we plan for TDI in LISA. Now, I just wanted to mention the more recent studies and the results. This is also a little bit of advertisement for all the talks that will be given during the symposium related more or less to TDI. And I will start with the search for all the combinations. So as I said, there's no known finite set of generators for the second generation TDI space. So the question is, can we find somewhat all of them in another way? Because some might have interesting properties. Maybe the sensitivity is a little bit different, or we want to use some of them to have a better estimate of the noise, these so-called null channels. And so in 2005, Michele Valisneri proposed an algorithm to find manually, I would say, all the different second generation combinations. So he started by expressing the necessary conditions for a combination to be valid based on this geometrical interpretation. And in the end, he found, he used a combinatorial algorithm to find the 16 link combinations, so all the combinations that use 16 links, and he found 48 of them, including the second generation TDI Michelsons, as that we mentioned before. This result was revisited more recently by a bunch of people from Trento, and they basically showed that there are other combinations that suppress laser noise to required levels for specific orbits. And you can actually learn about this a little bit more if you want by following the talk by Martina on Thursday on the effectiveness of null TDI channels to monitor the instrument noise in LISA. So some of them have interesting properties. Now, going more on the data analysis side, there has been some an interesting approach proposed in 2018, where basically you switch gears and using a time model problem, so with constant arms in the frequency domain, the idea is that you write the covariance matrix of your raw phase meter measurements, so your interferometric measurements. You don't perform TDI as a first step. And then you perform a principal component analysis on this covariance matrix. And if you do that, you will find some eigenvectors with very high eigenvalues and some of them with very low eigenvalues. And so if you have very low eigenvalues, that means that these eigenstreams are actually laser noise free. So that means that they're equivalent to TDI combinations, but you haven't computed them before. So you can write the likelihood directly in terms of the phase meter signals, somehow including or integrating the TDI step inside your likelihood. In a way, this generalizes the concept of these orthogonal combinations that we've talked before, A, E, and T, to arbitrary arm length and arbitrary noise correlations. And this idea has been extended very recently by Quentin et al. With a more realistic model where they perform the full parameter estimation, again with constant arms. And as, again, an extension of that, in the new paper, they showed that you actually can extract the arm length from this framework. So you don't need to estimate them with an independent method and feed that into your TDI algorithm before. And if you want to learn more about this, Quentin Bagui is given this presentation on Thursday about blind cancellation of laser noise for space-based gravitational wave detection. Hendry et al. In 2021 followed actually a similar idea quite among the same time, but in the time domain. So the idea is to model how the laser noise is entering the measurements in a time domain where you use a discretized description. So for example, for fractional delays, you use finite order filters. And you write this in a matrix. And in the end, the null space of this mixing matrix gives you basically these laser noise free quantities. And with a bit of algebraic manipulation, you can show that you recover the TDI-like combinations. Again, this has the advantage that it accommodates any arm length evolution, hence the name TDI generation infinity. Following this paper, there has been a lively discussion with Tinto et al. About the equivalence between this matrix-based approach and the original formalism of TDI. And I think, as a conclusion, we can say that there is actually an equivalence in the approximation of continuous data. Another aspect of TDI is this TDI ranging idea. So, as we said before, TDI basically consists in linearly combining time-shifted measurements. And the time shifts that you use are basically multiple of the light travel times along the LISA arms. And so TDI requires previous knowledge of the light travel times. The baseline right now is to use an onboard method to measure the absolute ranging. And you do this by modulating your laser beams with pseudo-random code. And then you correlate them, and so you can compare the different clocks on board the different spacecraft and deduce the light travel times. If you want to learn more about this, there's a talk given by Kohei about the status of pseudo-random noise, ranging performance, and optical data communication on Wednesday. But in 2005, Tinto et al. Noticed that actually, if you compute your TDI combination with arm length that are true, the right ones, the correct ones, the laser noise suppression is maximum. And if you make a little error on those delays, then laser noise is not as good. So you can use optimization methods to fit for these light travel times and determine the delays as an alternative to this baseline method based on pseudo-random noise. More recently in 2021, Jessica Page applied this using a Bayesian framework. And there's actually a continuation of this work that you can follow with a pre-recorded talk on Bayesian time delay interferometry for orbiting LISA by Jessica as well. So go ahead and watch that if you're interested. As a last point about TDI ranging, Martenstadt et al. Proposed to modulate a tone on the laser sources to increase the noise to signal ratio and therefore the TDI ranging performance. And this, if you want to learn more about this, there's going to be a live talk as well on Thursday by Martin about tone assisted TDIR for LISA. So that's a lot of references, but that gives you a little bit of ideas about how rich this field currently is. And my last slide about the new results and ongoing studies, it's about this noise reduction pipeline. So as we said before, TDI is only one of the many steps that's necessary to prepare the data before analysis. In all of these steps are gathered in this L0 to L1 INREP pipeline or pipelines. One of the main activities during the last LISA phase was to propose a baseline implementation or a demonstration of INREP. And if you want to learn more about this, Shweta is presenting on Wednesday a talk about this LISA data processing L0 to L1. And in 2022, there's been a paper from Olaf et al. That suggested that actually the order of the operations that you can perform inside these noise reduction pipelines actually matters. And so other pipelines are viable and should be explored. As an example, TDI can be carried out before we synchronize the measurements to a common time frame. and that might have a certain number of advantages. So if you want to learn more about it, on Thursday, Olaf is going to give you a talk about TDI without clock synchronization. And the last one, of course, all of these ideas about TDI need to be tested before LISA flies. And so there have been various numerical simulations to check laser noise suppression levels. Here are only a few of them. Michele used synthetic LISA to demonstrate laser noise suppression in 2019. Bayle et al. Checked that the LISA requirements were met with second generation combinations under some more realistic setups. And of course, also tabletop experiments, real experiments are carried over. LISA on table is one that uses electronic signals to simulate the optical beams and recombine them offline to check that TDI works. And the hexagon experiment is also used to check, for example, that the resampling, the clock issues with TDI can be solved. And if you learn more about it, Kohei is giving a talk on Wednesday about this hexagon experiment. All right. A few last slides about the perspectives and takeaways. This is going to be very short. So as I've tried to present to you, the activities around TDI and unequal arm interferometers have been going on for the last 25 years, where various theoretical aspects and approaches have been proposed. The connection between data analysis and TDI has been explored, and how we can merge them, maybe. The connection with other noise suppression algorithms as well inside INREP, the possible combinations, the exploration of the different TDI spaces, and how their transfer functions can be used for different things have been explored as well. And of course, simulations and experiments have been used to test parts of the algorithms. Launch date is still quite far in the future, and I expect that this field of research will stay active for the coming years, where more realistic cases will be studied, and of course concrete implementations and pipelines will start to be proposed. As my send away slide, I just wanted to talk about PyTDI, which is an open source package that proposed a concrete implementation of TDI in the time domain using time varying fractional filters. So if you're interested about using it with real data, you can attend the LDC workshop, actually, that I will be giving the first session on data generation later this evening with Mod later today. And I think now is the time for questions.
Thank you very much, Jean-Baptiste. That was an excellent tutorial on TDI. There have been 1 or 2 questions in the Q&A. One has been answered already, which was a question about how flexible the implementation of TDI is during the mission. And I think the answer was given by Oliver that of course it is, because it's a ground-based combination of data streams. So we're not committed to anything on board at the point of launch. The second one is more to do with the actual hardware, in a sense. It's a question about how critical is the clock noise and clock stability and clock synchronization between the spacecraft. Can you comment on that?
Yeah, of course. So as you probably know, there will be only 1 clock per spacecraft, and these clocks will not be actively synchronized between the spacecraft. And these clocks are responsible for quite a few things on board the spacecraft. One of them is to drive the ADC, so sample the data, and another one is to timestamp the data. And so any error, any jitters of those clocks translates into a jitter of the phase that you measure and the timestamp that you associated with these measurements. Thankfully, the clocks are not too good. They're really good, but they're not good enough to meet the requirements. So what we do is we modulate a signal on the laser beams that creates a sideband that we can use to correct for these clock errors as a additional processing step on the ground. So that's maybe a first answer. And another answer is that the timestamping errors that I talked about are important when you start to combine the different data. So TDI combines data from different spacecraft. And so if the timestamps are a little bit wrong, then you might make some errors. The good point is in this talk that I mentioned here, time delay without clock synchronization, you can show that basically the ranging that you measure contains the clock differences as well as the light travel times. So if you apply TDI directly using those ranging estimates, you cancel out the clock differences. Of course, as a last step, you want your TDI combination to be expressed in some astrophysical time frame, so you still need to resample everything to a common time frame. But the requirements are actually much less stringent because you don't care about laser noise suppression anymore. You only care about the timing accuracy of your waveforms, which is, let's say, of the milliseconds, which is easily attainable.
Thank you. I don't think we have any other questions at the moment. Hang on, there's one just appeared. No, it's a comment about another TDI talk. That there's a talk from Mauro Pironi on Thursday on the non-orthogonality of TDI channels. So I think we should point people to that too. But if there's no further question, could I thank you again, particularly for your presentation, but also all the speakers of this morning. It's been an excellent start to the symposium, and I would encourage you to go and refresh yourselves and return promptly at on the hour, which is just under 90 minutes from now. And then we'll start with the plenary block 2, which will be chaired by Kelly. So until then, goodbye, and we'll see you shortly.